Welcome to the second half. And so, Qiongling Li, she will continue her talk on harmonic maps for surface group representation.
So let's first consider just not a general Higgs bundle, but to consider SLNC Higgs bundle. It's a pair Phi, which is surely a Higgs bundle. We just put more conditions on it. First, E is a holomorphic vector bundle of rank n. We need its determinant 9 bundle is trivial. And secondly, our Higgs field phi from E to the E twisted by K as a holomorphic bundle map. We also add the condition as a trace equal to 0. So correspondingly, we consider our target space for harmonic map, which is smaller, not all the Hermitian positive definite Hermitian matrix that say positive definite Hermitian matrix of determinant 1. So from group point of view, is SLNC quotienting SUN. So from now on, this N is what we are going to consider. K is a holomorphic cotangent bundle. So yesterday I promised to you that I will explain the curvature formula. Now we are going to explain briefly. So at every point A in N, we can identify its tangent space as the part I denote as PA, as the space, vector space of Hermitian matrices, which is with respect to our A. Just not the standard Hermitian, but Hermitian with respect to A. So the identification is by taking Y to the A inverse Y. I think possibly I need this minor sign, but I want to check. After this identification, we can say what's the curvature formula for this space N. So the formula for the sectional curvature of the plane, tangent plane, spanned by two vector y1, y2, which I already identified them as in PA. So this plane, its curvature is equal to trace of y1, y2, y1, y2. Quotient y1, y1's norm times y1, or y2, y2, minus y1, y2 norm square. So this is just the standard formula for the curvature in symmetric space. So in our case, for the equivariant harmonic map, F from the universal cover of our Riemann surface into N, we want to see the sectional curvature of the tangent plane at some point fx. Sigma. So let me also say it's calculated in n. So the curvature for sigma is just the curvature for this two tangent vector span the plane, which is fx and fy. But we already have the identification as if we want to apply this curvature formula, we need to see y1, y2. So this is, in fact, we need to use identification. Here is f inverse fx and minus f inverse fy. This is the right place to apply the formula there. But we already have the lemma from yesterday that there is a close relation between the Higgs field and our f inverse df. So the lemma from yesterday is psi h equal to minus 1/2 f inverse df. So in particular, our psi h is phi and phi star. So here we just put inside, this is the psi h evaluate on dx. This is the psi h evaluate on dy. And you just plug everything in. I think you can believe what the formula we can get purely expressed in terms of phi and phi star. So this is the trace of phi star square over trace of phi star square minus trace of phi square norm square. So this curvature, let's say in n, by Gauss formula for harmonic maps from two-dimensional surface. We have that the pullback matrix curvature. This is really the curvature on the surface. It's always smaller than this curvature for this tangent plane calculated in n. So there is a remark that if we look at this formula, we always see it's less than 0, just because actually we know that this thing is negative. So, but I don't explain it. So actually, we always know this is less or equal to 0. So now I'm going to explain several more things about Higgs bundles. And after that, I will talk about some selected topics on harmonic maps. So first, recall, given a stable Higgs bundle, if there exists a unique Hermitian metric H such that we have a new connection coming from the Chern connection plus phi and phi star is flat. But we look at the flat condition, it's just the d composed d equal to 0. And equivalently, we are actually asked H solving an equation, which is the curvature for this Chern connection plus phi and phi star equal to 0. So this is called a heating equation. So now I'm going to introduce the modular space. The modular space denoted as Higgs is all the polystable, which is the direct sum of stable ones of, here I should say degree 0. Here is also degree 0. But I'm actually saying SO and C Higgs bundles. So quotienting gauge equivalence. So this is our first space, modular space of Higgs bundles. And the second space is the Theorem modular space. This is all the reductive SL and C flat connections. So of course, it's always on some bundle. We just don't really say the bundle. So this is also quotient gauge group. And here the reductive is just also the direct sum of the irreducible ones. And the last thing is the representation variety. It's denoted as a representation from our, so this time I use S. S is the underlying topological surface of X. Okay. To SL and C. So this is also reductive representation. And here is quotienting the conjugation action by SL and C. So yesterday we actually explained the relationship between these three spaces, like set-wise. So we explained from a representation, we can get a flat connection, and then we can decompose the flat connection into Higgs bundles using the harmonic map or harmonic metric. And it also can go back using that statement. So this is the non-binary Hodge correspondence. So it's just from the modular space of a Higgs bundle to modular space of flat connections, which is also goes to the representation variety. So mainly we have E phi here, and we get a flat connection D here, and then we go to holonomy of this flat connection D. And all this modular space are actually homeomorphic with the right topology. And then to talk about the next things, we really need to explain several concepts about the modular space of Higgs bundles. The first thing is the heating vibration and the heating section. So we have H from the modular space of Higgs bundle to the heating base, which is quadratic differential, cubic differential until n differential. So I is from 2 to n, where Q2, Q3 to Qn is an element. And we have E phi goes to some polynomial acting on phi to Pn of phi. Because the left-hand side, we have this phi, E phi lies in the gauge orbit. So our polynomial should be conjugation invariant. So here this Pi SLNC invariant homogeneous polynomial of degree I. But note that no matter what kind of polynomial we choose, this P2 phi is always some constant times trace of phi square. Basically, there are no other choice. But if you remember yesterday's our formula, this trace phi square appears. So recall the pullback metric is equal to 4 trace phi square, dz square, plus trace of phi star of dz bar, plus dz bar dz, and plus the conjugation. Okay, so that means we do see trace phi square in the pullback matrix 2-0 part. So i.e., the pullback matrix 2-0 part is 4 trace of phi square, depending on whether we remember dz square or not. And this is actually called, this is the definition, the Hopf differential of the map F is the pullback matrix 2-0 part. So that means this heating vibration, this differential has some meaning, at least for the first entry. The first entry always a constant multiple of the Hopf differential of the associated harmonic map. So it has a geometry there. But we don't have the corresponding meaning for the other differentials. The downstairs? Yeah, okay. So this line will be saying the Hopf differential of the map F is the pullback matrix 2-0 part. So which is in fact the trace of phi squares times 4. And we also need to remember one thing is how about at the special point, that is all this differential vanish. The inverse image of 0 point is a special fiber. So that's the most singular fiber of all these fibers. And in fact, all the topology of the modular space of Higgs bundle is encoded in this single fiber. So this is called the Neopoldon cone. So if we choosing the PIs in a nice way, we can define an explicit section of this heating vibration. It's defined as follows. The section S, because I will use S a lot. So S of Q2 to Qn, we can write down the explicit heating and the Higgs bundle. The E is k to the n minus 1 halves to k to the n minus 3 halves, just decrease by 1 until the end to get a rank n bundle. And the Higgs field, so because we want to get a holomorphic bundle map from E to the E traced by K, so at each entry, we actually know there are differentials, at least from some K some power to K some power. So we have phi defined as the downstairs as R1, R2 to Rn minus 1, and all the down is 0. And upstairs is Q2, Q2 to Q2. And here is Q3 to Q3 until the last one is Qn. And this Ri, just a constant. This is some kind of normalization, because I want all these Q2 have the same coefficient, so I just put all coefficients on this side. So it's just write a Higgs bundle purely using the data as Q2 to Qn. So heating shows that the image of this heating section under this non-abelian Hodge correspondence. So it maps into representation space, have a holonomy in SLNR. So not just in SLNC, but actually goes into SLNR. Moreover, it's a connected component of the representation variety for SLNR. And call it as a heating component. So we can use this heating component to refer as Higgs bundles as in heating section, or just the representation in this representation variety. And elements inside this component is just called a heating representation. But we also need to note that we can specify some special points. For example, S0, 0 of 0, which is just the 0 point. So it's after the non-abelian Hodge correspondence, it corresponds to a representation which is explicit. So this is a tau n composed with J0, where J0 is from surface fundamental group into SL2R. The uniformization representation of our Riemann surface X. And then this tau n is from SL2, we can say just the C, to SLNC, the unique irreducible representation. So it's just this point, it's nothing else, just the original uniformization representation of our base Riemann surface. but maybe not this special, but still special with this Q2. Okay. So if we allow this Q2 non-zero, it also corresponds to something coming from this SO2R. It's just not necessarily this J0. It corresponds to tau n composed with J, where J is from 1 to SL2R function. So we can give another definition for heating component inside this representation variety, that the representations are the ones which continuously deform to such image of Teichmüller space. The last thing is there is a natural C-star action on the modular space of Higgs bundles, which is quite unique for the Higgs bundle side, because you don't see in the representation side. So for T, times E phi, let's write the gauge equivalent class. So it's just the E times T phi. Just very simple. So finally, let's get to talk about some selected topics. But I want to point out that because of time limit and my own knowledge limits, I cannot cover all the interesting topics. So I only choose some topics which I'm most familiar with. So I just choose some of it. So this selected is not a good selection. Okay. So these topics will contain 2 lines. The one main line is consider this a C-star action. We consider first the T goes to infinity. How about the harmonic map Ft? And then along this C-star flow, how about this Ft? Like say something along C-star flow. And then the next is T goes to 0. How about Ft? So this is one line for the topics here. And the other line is about the relationship between heating fiber and the harmonic map Ft. So the first topic is about T goes to infinity, which is also just asymptotics. So let's first give a definition. Denote by D of E phi the set of points on the Riemann surface X such that the Higgs field fails to have n distinct eigenvalues. Just this is a pointwise version, so we can talk about the eigenvalue at each point. So if we get rid of this set, we can take a universal covering pi from y to x minus this set. So then we can consider the pullback Higgs bundle. Let's remember the holomorphic structure. So this now comes back to y. And then we have this Higgs bundle decomposed into 9 bundles. And eigenvalues. Let's say Phi as one form times identity on EI. Where EI, rank of EI is 1, and Phi are holomorphic one forms. So because we already get rid of this bad set, we can make sure now this Phi, Pj never equal for different ij. So this Phi minus Pj is never vanishing for I not equal to j. Given by the eigenvalue. Let me see. Yeah, I think it's written as a universal cover. Maybe I should check. But it's just I need to have this decomposition. I think special cover works. Okay, maybe I should go on. Okay, thank you. So now we consider any path in this Y be a smooth path. So we have the expression of this Phi. Phi on Y, we put back on this 0, 1 interval. It becomes alpha I S ds. Alpha I is a smooth function on the interval. And now we need to consider some special paths. A path gamma is called non-critical. If the real part of alpha IS and the real part of alpha JS never equal. So this is a strong condition on this path for every point in this interval. And we can define this as, denote this as AI. Maybe later. So let's reorder that's the real part of alpha IS in a decreasing way. Because this condition is uniform for S, a decreasing way. So then we can denote alpha AI as real part of alpha IS after this reordering. Okay. So we have A1 greater than A2 greater than AN. So lots of preparation right now. Let's first say the conjecture and explain one more notation in the conjecture. The conjecture is called the heating WKB problem. By Kazakov, No, Pandit, and Simpson, is saying as t goes to infinity, the associate, so this t goes to infinity is the family for the Higgs bundle. For this family, t goes to infinity. So we have corresponding harmonic maps, Ft, it satisfies for a non-critical path. We say for any non-critical path, gamma we have the vector distance between the image of gamma 0 under this Ft and gamma 1 under this Ft is approximately as A1, A2 to AN. So I will explain this distance soon. But just look at this conjecture. On the left-hand side, it's depending on the Higgs bundle itself. But on the right-hand side, this A1, A2 to AN, it's not about the Higgs bundle, it's only about the image of the Higgs bundle under the heating vibration. Because it only sees the eigenvalues. The heating vibration is a way to, it's just seeing the eigenvalues, nothing else. So this kind of forgetting, if we just look at F for some particular t is not true, but as t goes to infinity, it's forgetting about the fiber. It's only see what's the heating base. So here we quickly define what's this vector distance. Is let phi be a n-dimensional vector space, complex vector space for two Hermitian matrix H1, H2 on V. We have a vector distance between these two matrices. That means 2 points in the N. So we can take a basis, take a base E1 to En of V, which is orthogonal to both H1 and H2. So we can always do that. Then we have real numbers, the kj defined as ej measured in H1, and then ej measured in H2, and then we both take log. And again, reorder it. Such that k1 greater or equal to k2 to kn. And this is our distance. The theorem by Mochizuki suppose if E is some condition here, so this is a generically regular semi-simple. So I don't know why he called this the name. I think he invents this name, but actually this is very generic. It's not you have three things to give conditions, but it's very generic, and we are going to explain it. But if we have this condition, then if gamma from 0, 1 to y is non-critical, then there exists a constant C0, epsilon 0, both are positive, such that we have 1 over t of distance between ft of gamma 0, ft of gamma 1, minus a1 to an. I think I would lose 2 here. There is 2. Is less than C0 times the exponential of minus epsilon 0 t. So it's just, they are not just asymptotic to each other, they are actually asymptotic in the rate exponential to t. Yes. And this condition, suppose I have a t phi, then along this t, I say along t times e phi, this family. Yes, there's always this star flow, and then I want t goes to infinity. Yeah, this is that meaning. So let's explain what this condition is. It's very simple. A condition of a Higgs bundle is so this is generically regular semi-simple. If the set we define there, just the points where phi fails to have n distinct eigenvalue, if this set is finite. Okay. So this is a very clean condition. For example, for or SL to C Higgs bundles, we can see this condition is quite general. That means if phi is either in the nilpotent cone or is satisfying this condition. And then, so for the Higgs bundle in the nilpotent cone, there is no such question, as we don't need to ask the question for those Higgs bundles, because it never goes to infinity. It always stays in the nilpotent cone. So at least for the SL2C Higgs bundles, this already solves everything. But why this is true? This is because for Higgs bundle phi, for the Higgs field phi, if we say its determinant is Q2, then it always has two eigenvalues. Square root of Q2 and minus square root of Q2. So this bad set is just the points, the zeros of Q2. So either Q2 vanish, in that case, it's in the nilpotent cone. Or if Q2 not vanish, it always has finite zeros. So that means it's in this condition. So let's say the key estimate is a proposition under the same assumptions. Take any neighborhood N0 of this bad set. There exists C0, epsilon 0, positive constant, such that on x minus this N0, we have the chain connections curvature. Its norm with respect to the metric on E and the metric on the surface is equal to T squared times phi and phi stars T is always less than C0 exponential of minus epsilon T. So it's always first to show this curvature formula. So this is really saying the original heating equation is the sum of the chain connection curvature plus the Higgs fields and its dual Lie bracket. That's the original heating equation, saying their sum equal to 0. But here saying if T goes to infinity, these two parts decouples. They are individually exponential decay to 0. So the remark is for n equal to 2 case, there is much more complete work. In that case, like, we don't need to give a restriction as a non-critical path. We can talk about any path, and then talk about the distance of the image of harmonic maps. So this is first by SL2R by Wolf. SL2C is by Laplace Yeah. And Wentworth, so okay. Those two below and Wentworth. So basically, this heating WKB problem is a generalization of this result, but in a weaker way, because right now it's only about the non-critical path. And for n equal to 3 case, for the heating section S0, Q3, so for this kind of Higgs bundles, is by John Lofting. And then for general n, which is also for the heating section, for Qn, and for Qn minus 1, is by Brown Collier and Wu. So what's still open? The first is a complete description. That means we get rid of conditions on Higgs bundles, because right now the Higgs bundles are still not the full family. So to give a characterization of other non-generic families. And secondly, is for general paths. So second topic is negative curvature. So this is more just for heating section. So the conjecture is for any heating representations. And we can also fix a Riemann surface, sigma, let's say x. Then the unique row equivalent harmonic map f from x theta to n has the property that it's never tangent to a flat in N. That means the tangent plane to this harmonic map always has a strict negative curvature. So in terms of the curvature formula we talked about in the beginning of today, this conjecture is equivalent for every Higgs bundle in the heating section. We have the chain connections curvature is never 0. And the Higgs field and its Hermitian joint, Lie bracket is never 0. Because we already see before the curvature the upstairs is trace of this term square, And that's kind of negative of this term's norm square. The only time it's vanished is this term vanish. So we can see this is kind of a very different behavior as this asymptotic behavior. That's saying every place it's going to be decoupled. But here we say for heating section, it's never decoupled. So this implies if conjecture is true, will imply the pullback matrix curvature is always strictly less than 0. And then what's the known case? Is still for the heating section at the Sachi family. And in fact, we can ask, how about for the maximal representations? Even though we never talk about it, but I just say maximal representations are very similar to heating representations in many ways. So normally, if we have some conjecture on heating representation, we should ask the same question for maximal representations. So the next topic is about heating vibration and harmonic maps. Let's write the conjecture A inside each heating fiber. The heating section maximize the energy density. So we should say over the corresponding harmonic maps. So immediate corollary of this conjecture is that if we have this energy density functions domination, we can immediately say the pullback matrix domination. That is because the energy density function is the 1,1 part of the pullback metric. For the 2,0 part of the pullback metric is the Hopf differential. But being in the same heating fiber, that means they have the same Hopf differential. So that's the conjecture of the corollary of the conjecture is saying inside each heating fiber, the heating section maximize the pullback metric. of associated harmonic maps. So in fact, if you look at this conjecture, it's very hard. This is about comparing functions greater than another function. So how about we consider not this energy density function, but we consider an integral version, a weaker conjecture. Still inside each heating fiber, the heating section maximizes the energy. So this is just a number. And if we say not just maximize, but is the only maximum in the heating fiber, if in that sense, just we say strictly maximize, we can actually say, we can define heating section which are the maximum of the energy. This is a purely intrinsic definition for heating section, not as previous we build this section. So it actually has an intrinsic property. So what's the known case for n equal to 2? This is by Duan and then Polazan. And then for general n, for heating fibers, inside the heating fiber, at Q2, 0, 0. The conjecture A is true. So note that for n equal to 2 case, it's not a special fibers, it's all fibers. Then this theorem 1 will give us topological conclusions. So the corollary will be saying any representation as coming from holonomy of a Higgs bundle inside the heating fiber at Q2, 0, 0. It is either the image of Teichmüller locus or is strictly dominated by tau n composed with J, where this J is the fiction representation such that F from x tilde to H2 the J equivalent harmonic map has a Hopf differential Q2. So this is just this J encodes information of this Q2. So let's say what's the proof of Theorem I. So step 1, showing that if the curvature for the tangent plane in the target space is always at least of -1 curvature. So this is after renormalization. So this one is such that if Q2 vanish, it's really -1. So if this happens, then the proof follows from the original proof of Diwan and Tonozon for the n equal to 2 case. So because in that case, in n equal to 2 case, this is always equal to -1 because our target space is H3. But for their proof, there is no need saying it's equal to -1. That's the less or equal to -1, and everything works well. So what's really in this generalized version, n greater than or equal to 3, we need to show this curvature is always less than -1. And then we want to say, for a Higgs field sharing the same heating fiber with such representations, it will have this property: its curvature is always very negative. And more explicitly, so note that for phi in the heating section for this Q200, so that means phi equal to 0, 0, and R1, R2 to Rn-1, Q2 to Q2. So for such a Higgs field, we can calculate its eigenvalue. So eigenvalues of phi are very explicit. It's just n-1 square root of Q2, n-3 square root of Q2 to 1 minus n square root of Q2. So this is everything we get from E phi in the fiber at Q2, 0, 0 will have the property that its eigenvalues are always like this. So we are going to use this property, and this is the only property for a Higgs bundle inside this fiber. So the key lemma for Consider the space O as or matrix in SL and C having eigenvalues as t times n minus 1, n minus 3 until to 1 minus n. Then the function m hat m on O to R, taking A to A and A dual, trace square over trace of AA dual square minus trace of A square has a critical point at some A0 if and only if A0 and A0's dual generates a principal SL2C. So this generation is the algebra generation. So I want to say this lemma is actually a generalization of all the theorem in GIT theory by Nina Less. But for nilpotent matrix, it's saying as follows: for any non-zero nilpotent element, the function from the orbit of A goes to R. So the orbit is the conjugation orbit of A, which is the adjoint orbit of the algebra element. Taking a matrix X to trace of X dual square, quotienting trace of X dual square minus trace of X square has a critical point at X0 if and only if X0's dual and its lip bracket is an SL2C triple. So we are just generalize this nilpotent property to something as similar as a copy of SL2C, but not necessarily nilpotent. So this is a pure algebraic calculation. So it's just saying if we have some algebraic conditions on the Higgs field, we can actually get to conditions on the curvature. Probability 4 is a C-star flow. The conjecture here is a non-C-star flow. The energy density of associated harmonic maps decreases as the norm of T decreases. So this is a relationship between the harmonic maps and the C-star flow. And we can also ask a weaker version. So we can ask two weak versions. The first weak version is how about energy? Just 1 minute. Okay. So the first weak version is energy, which is again the integral question for this one. And in this case, it's actually known. So for energy, it's true. This is by heating. So it's a strong evidence for this, even though it jumps a lot from the integral version to pointwise version. And for the second conjecture, is maybe asking monoticity is too much. To talk about for the energy density for one Higgs bundle is greater than its limit to 0. So this is not a monoticity question, it's a domination question. And then there are also evidence saying this should be true. At least for example, for heating section, this last conjecture is true. And we actually working with Brian, we know that for the maximal representation and the other higher Teichmüller space is also true. But for the first one, we only solve for with the Song-Dai, we only solve for the cyclic Higgs bundles. But there are lots of questions unknown. That should stop here.